When planning a 200 amp underground electrical service, several factors need careful consideration to ensure a safe and code-compliant installation. Firstly, selecting the appropriate conduit is crucial. A 2-inch Schedule 80 polyvinyl chloride conduit is generally a suitable choice for underground runs. Schedule 80 offers enhanced strength and durability compared to Schedule 40, providing better protection for the conductors against physical damage from rocks, soil compaction, and other potential hazards. The strength of Schedule 80 polyvinyl chloride is particularly important in areas where heavy loads or vehicular traffic might be present above the buried conduit. Secondly, conductor sizing is essential for handling the anticipated load. 3/4/0 American wire gauge aluminum conductors are typically sufficient for a 200 amp service. However, it is vital to verify this with ampacity tables found in the National Electrical Code, specifically Table 310.15b16 or its equivalent, depending on the specific code cycle being followed. These tables provide ampacity ratings for various conductor types and sizes based on insulation temperature ratings and installation conditions. Aluminum conductors are a common choice for underground services due to their lower cost compared to copper, but it's important to account for their higher resistance and voltage drop over long distances. Conduit fill is another critical aspect to consider. The National Electrical Code mandates that conduits should not be filled to more than 40% of their internal capacity. This limitation is in place to facilitate heat dissipation from the conductors and to enable easier wire pulling during installation and future maintenance. Exceeding the 40% fill rate can lead to overheating of the conductors, potentially causing insulation damage and increasing the risk of electrical faults. To calculate the conduit fill, you'll need to refer to Chapter 9, Table 1 of the National Electrical Code, which provides the dimensions and cross-sectional areas of different conduit types and sizes, as well as the cross-sectional areas of various conductors. Bends in the conduit run also require careful attention. The National Electrical Code restricts the total number of bends in a single conduit run to a maximum of 360 degrees, which is equivalent to 490-degree bends. This limitation is intended to prevent excessive pulling force on the conductors during installation, which can damage the insulation and reduce their lifespan. Each bend increases the friction between the conductors and the conduit, making it harder to pull the wires through. Using sweeps, or long radius bends, instead of sharp 90-degree bends can help reduce friction and pulling force. The minimum depth at which the conduit must be buried is also regulated by the National Electrical Code. Generally, underground conduit should be buried at least 18 inches deep. This depth provides adequate protection from physical damage due to digging, ground movement, and other potential disturbances. However, the required burial depth may vary depending on the specific application and local codes. For example, if the conduit is installed under a roadway or in an area subject to heavy vehicular traffic, a greater burial depth may be required. The National Electrical Code Table 300.5 outlines the minimum cover requirements for various wiring methods and voltages. Backfilling the trench properly is essential for protecting the conduit and conductors. The trench should be backfilled with compacted earth or sand to provide a stable and supportive environment. Compacting the backfill helps prevent settling, which can cause stress on the conduit and conductors. It also minimizes the risk of damage from sharp objects in the soil. Using sand as a backfill material provides a cushion around the conduit, reducing the likelihood of abrasion and other forms of physical damage. Warning tape should be installed above the conduit to alert anyone digging in the area to the presence of underground utilities. This tape is typically brightly colored and marked with a warning message such as "Caution electrical line below." It should be buried approximately 12 inches above the conduit, providing sufficient warning before anyone encounters the conduit during excavation. Concrete encasement may be necessary in certain situations to provide added protection for the conduit. This involves encasing the conduit in a layer of concrete which provides a physical barrier against damage from digging, ground movement, and other potential hazards. Concrete encasement is commonly used in areas where the conduit is subject to heavy loads or where there is a high risk of damage. Pulling the wires into the conduit requires careful technique to avoid damaging them. Lubricating the wires with a wire pulling lubricant reduces friction and makes it easier to pull them through the conduit. It is also important to use the correct pulling equipment and to avoid pulling the wires too hard, as this can stretch or damage the insulation. Using multiple pulling points can help distribute the pulling force and reduce the risk of damage. Labeling the conduit and wires is essential for easier identification during future maintenance or repairs. The conduit should be labeled at each end and at any intermediate points where it is accessible. The wires should be labeled at each termination point with their circuit number or function. Clear and accurate labeling helps prevent confusion and ensures that the correct wires are identified during troubleshooting or repairs. Finally, a thorough inspection by a qualified electrician is necessary to ensure that the installation meets all applicable codes and standards. The inspection should include a visual examination of the conduit, conductors, and terminations, as well as electrical testing to verify proper grounding, insulation resistance, and circuit integrity. Any deficiencies identified during the inspection should be corrected before the service is energized. Consider voltage drop, which is the decrease in voltage along the length of the conductors due to their resistance. Over a long distance, such as 250 feet, voltage drop can become significant, especially with aluminum conductors, which have a higher resistance than copper. The National Electrical Code recommends limiting voltage drop to no more than 3% for feeders and 5% for branch circuits. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by circular mils, where K is the direct current constant, which is approximately 12.9 ohms circular mils per foot for copper and 21.2 ohms circular mils per foot for aluminum. I is the current in amps, D is the one-way distance in feet, and circular mils is the cross-sectional area of the conductor in circular mils, which can be found in the National Electrical Code Chapter 9 Table 8. If the calculated voltage drop exceeds the recommended limits, you may need to increase the size of the conductors to reduce their resistance and minimize voltage drop. Grounding is a critical safety aspect of any electrical installation. The grounding system provides a low impedance path for fault current to return to the source, which helps to trip over current protective devices, such as circuit breakers or fuses, and quickly de-energize the circuit in the event of a fault. The grounding system must be properly sized and installed in accordance with the National Electrical Code Article 250 to ensure its effectiveness. This includes the grounding electrode conductor, which connects the grounding system to a grounding electrode, such as a ground rod or a metallic water pipe. Surge protection can protect sensitive electronic equipment from voltage surges caused by lightning, utility switching, or other disturbances. Surge protective devices, or SPDs, are designed to divert surge current to ground, preventing it from damaging equipment. The National Electrical Code Article 230.67 requires surge protection for dwelling unit services. SPD should be installed at the service entrance and may also be installed at downstream panels or individual equipment to provide additional protection. Coordination of overcurrent protective devices, such as circuit breakers and fuses, is essential for ensuring that the electrical system operates safely and reliably. Coordination means selecting and setting the overcurrent protective devices so that the device closest to the fault will trip first, isolating the fault and minimizing the impact on the rest of the system. This helps to prevent nuisance tripping of upstream breakers and ensures that power is maintained to unaffected circuits. Time current curves, or TCCs, are used to analyze the coordination of overcurrent protective devices. These curves show the tripping characteristics of different devices under various fault current conditions. The National Electrical Code Article 240 provides requirements for overcurrent protection and coordination. Short circuit current rating, or SCCR, is the maximum fault current that an electrical component or assembly can safely withstand without sustaining damage. It is important to ensure that all electrical equipment has an adequate SCCR for the available fault current at its point of installation. If the available fault current exceeds the SCCR of the equipment may fail catastrophically during a fault, posing a safety hazard. The available fault current can be calculated using engineering methods or obtained from the utility company. The National Electrical Code Article 110.9 requires equipment to be suitable for the available fault current. Bonding refers to the practice of connecting all metallic parts of the electrical system together to create a low impedance path for fault current. This helps to ensure that all metallic parts are at the same potential, reducing the risk of electric shock. Bonding is particularly important in areas where there is a high risk of moisture or corrosion, such as underground installations. The National Electrical Code Article 250 provides requirements for bonding. Using proper connectors and terminations is essential for ensuring reliable and safe electrical connections. Connectors and terminations must be listed for the specific type and size of conductor being used and must be installed in accordance with the manufacturer's instructions. Improperly installed connectors and terminations can lead to overheating, arcing, and even fires. Antioxidant compound should be used on aluminum conductors to prevent oxidation, which can increase resistance and lead to connection failures. Torque requirements are critical for ensuring that connectors and terminations are properly tightened. Over-tightening can damage the connector or conductor, while under-tightening can result in a loose connection. Torque specifications are typically provided by the connector manufacturer and should be followed carefully. A calibrated torque wrench should be used to ensure that the correct torque is applied. Expansion and contraction of conduit and conductors due to temperature changes can cause stress on the system. Expansion joints should be installed in long conduit runs to accommodate this movement and prevent damage. The National Electrical Code Chapter 3 provides requirements for expansion joints. When working with underground electrical installations, it is essential to take precautions to protect against moisture and corrosion. Direct burial rated conductors should be used, and connections should be made in waterproof enclosures. The use of corrosion-resistant materials, such as stainless steel or coated aluminum, is recommended. Identifying and marking the underground service is important for future reference and to prevent accidental damage during excavation. The location of the service should be clearly marked on site plans, and warning signs should be installed to alert workers to the presence of underground utilities. As-built drawings, which show the exact location of the underground service, should be created and maintained for future reference. Communication with the local utility company is essential for coordinating the installation and ensuring that it complies with their requirements. The utility company may have specific requirements for the service entrance location, metering equipment, and grounding. It is also important to notify the utility company before energizing the service. Obtaining the necessary permits and inspections is essential for ensuring that the installation complies with all applicable codes and regulations. The permitting process typically involves submitting plans and specifications to the local building department and paying a fee. Inspections are conducted at various stages of the installation to verify compliance with the code. Failure to obtain the necessary permits and inspections can result in fines, delays, and even the removal of the installation. Safety is paramount when working with electricity. Always to energize circuits before working on them and use appropriate personal protective equipment such as gloves, safety glasses, and insulated tools. Follow safe work practices and comply with all applicable safety regulations. If you are not qualified to perform electrical work, hire a licensed electrician. Trenching safety is also critical when installing underground services. Always call 811 before digging to locate underground utilities. Excavate trenches safely following OSHA requirements for shoring, sloping, and benching. Never enter an unprotected trench, as it can collapse and cause serious injury or death. Consider future expansion when planning the underground service. It may be wise to install a larger conduit or pull extra conductors to accommodate future loads. This can save time and money in the long run by avoiding the need to replace the service later. Record keeping is essential for maintaining a history of the installation. Keep records of all permits, inspections, drawings, specifications, and test results. This information can be valuable for future maintenance, troubleshooting, or modifications. Finally, Continuous learning is important for staying up to date with the latest codes, standards, and technologies. Attend training courses, read industry publications, and participate in professional organizations to enhance your knowledge and skills.